In classical geometry, the geometric figure called an ellipse is defined to be this way. I'm going to put a point down in the plane. I'll call that a focus. There's going to be two of them, so the plural of that is foci. There'll be another one here. The definition of an ellipse is the collection of all points in the plane so that the distance from the point to this focus plus the distance of the point from this focus takes on some constant value. It turns out we can easily physically draw a picture of this situation. First, I'm going to put push pins in at the location of the two foci. Assuming I don't put too much stress on my little mechanism here, the distance between these two push pins will be the same as I maneuver my point around that I'm about to manufacture. I've made a little loop of dental floss here. It was the easiest source of string that I could find. If I were to hold the string tight, this distance is a constant. If I add in this distance and then add in this distance, I would have the circumference of the piece of string, which is a constant. Since these 2 points are not moving around, that would mean that this distance plus that distance would be the total length of the bit of string minus the distance between the foci. So in this way, as long as I keep the string taut, no slack in it, this distance plus that distance will be a constant, and if I draw in such points, what I'll draw in will be points of an ellipse. This may slip on me here, so I may have to restart this. If I pull too hard on the string, that happens. But if I don't pull hard enough, the string won't be taut, no slack. So this is a little fiddly here. So I'll end up with some shape like this. It's kind of like a circle, except instead of having a center, it has two foci. It looks like this is going to be very symmetrical, just as a circle is. If I take my thumbtacks out, my push pins, and set them aside, the straight line that contains the two foci, I'll only draw enough of this to reach the beginning and end of my ellipse. That straight line is called the major axis. It's always going to be the axis upon which the foci lie. Depending on how I'm trying to describe this, I might take that straight line to be the x-axis, or I could take it to be the y-axis. Either way, if I want to take advantage of the symmetry of the situation, the other axis at right angles to the first one, if I've got any sense, I'll put the place where it cuts across the first axis halfway in between the two foci. We'll call that the minor axis. Half of the major axis is called the semi-major axis. Half of the minor axis is called the semi-minor axis. And the idea is that any point on this curve that I've drawn will obey the following property. That distance plus that distance will be a constant. So this is the geometry of the situation. Now I want to turn this into an algebraic formula so that we can describe these ellipses with equations and formulas and numbers and such things. To start with, I'll make the major axis, the long axis, the x-axis, and the minor axis, the y-axis. I'm going to call the distance between the two foci I can pick any letters or symbolism I care to use, but it's going to turn out that the algebra works out most nicely if I call the distance along the x-axis 2 times c, so that this will be x-coordinate c, this will be x-coordinate negative c. The point on my ellipse will generically be called xy, and I want this distance plus that distance to add up to some constant value. I'll make up a special name for that constant value also. It'll turn out this has a geometrical significance in the end. Right now I can think about it just as making the algebra that I'm going to have to do a little bit nicer. So I'm going to say that d1 plus d2, I'm going to call that 2 times a. Because of the triangle inequality, this distance, which is 2c, must be no more than that distance plus that distance. So 2c needs to be less than 2a, which tells me that c is less than a. That is to say, a is bigger than c. I'll need to know that at some point. This will be important to me. The distance from the point xy to the focus that's more to the left can be calculated using the distance formula. We take the difference of the x's, square it. We take the difference of the y's, square it. Add those together, do the square root. In a similar way, we see that the distance from xy to c0 is radical x minus c squared plus y squared. The equation for my ellipse, then, is that the sum of those two distances has to equal 2 times a, and remember, a has to be bigger than c for this to make sense. In what follows, there's going to be a great mass of algebra. Basically, I'm going to isolate one of these radicals on one side of the equation, square both sides, simplify. There'll be a radical left in what I have. I'll isolate it, then simplify some more, and then we'll make use of the fact that a is bigger than c in a moment. Isolate a square root, square both sides, multiply the squares out. Notice that there is a plus y squared on both sides, so I'll just stop writing that down. Expand the squares out. Notice that there is a term x squared here and a term x squared there. Subtract x squared from both sides. Those terms go away. The same thing happens with the c squares. Add 2xc to both sides. Then observe that all terms have a factor of 4 so that you can get rid of the 4. Isolate the remaining radical factor. Square both sides again. Notice that negative a times negative a is the same thing as a squared, and in the other factor on the right, the radical sign simply disappears. Simplify some more. Notice that on both sides of the equation you are subtracting 2xca squared, so if you add 2xca squared to both sides, that term disappears. Subtract a squared c squared from both sides. Also subtract x squared c squared from both sides. This is the point at which it's crucial to know that a is bigger than c, meaning a squared is bigger than c squared, meaning a squared minus c squared is a positive number. A squared minus c squared could be thought of as the square of some other positive number. I'm going to make up an abbreviation for that. I'm going to call a squared minus c squared by another name. I'll call it b squared. This b will have some special significance to us, but for right now, it's just an abbreviation for a squared minus c squared. Taking advantage of that abbreviation, a squared b squared is the same as b squared x squared plus a squared y squared. Dividing through by a squared times b squared and simplifying, we finally get the equation of the ellipse with center at the origin, foci located on the x-axis, is x squared over a squared plus y squared over b squared equals 1. If you think about replacing x with negative x, y with negative y, or both, you'll see that this graph is going to be symmetric about the y-axis, the x-axis, and the origin, which is pretty much how we figured it was going to be because of the way we set our picture up. X squared over a squared is positive and gets larger as x gets further away from 0 in either the positive or negative direction. Same story for y squared. This means there are going to be strict limitations on how big x and y can be, and so we'll figure out what these things mean to us now. If I made the y equal to 0, that says that x squared over a squared is 1. That says x squared is a squared. That says x is equal to a, or x is equal to negative a. If x is 0, then that says y squared over b squared has to be 1. Y is either b or negative b. And we've seen by drawing the picture mechanically that, generally speaking, that's the kind of shape you're going to get. The foci are at x equals c and x equal negative c, which are closer to the origin than x equal a or x equal negative a, respectively. The b has a direct significance now. It's the y-intercept of the graph. We also have an algebra significance. The eccentricity of an ellipse is 2a, the length of the major axis, divided by 2c, the distance between the foci, and obviously you can cancel a 2 out. The eccentricity is c divided by a. This is how we're going to describe an ellipse with center at the origin, major axis along the x-axis, and x equals c, x equal negative c for the foci. Also, the eccentricity is c divided by a.